So let me assume that I've thrown the die twice. So if I want to calculate the probability with which I get 2 on the first throw, which means I get x1 equals 1, and I get an even number on the second throw, x2 equals 1. So let me also denote that this happened first by adding another number here. So this would be the first throw and this would be the second throw. So by Bayes' theorem, what we actually can calculate is joint probabilities like this. So a probability like this, where you want to calculate the probability with which two events would occur, would be given as probability that x11 would be 1 multiplied by the probability that x22 would be 1, given that x11 is 1. So you can think of it intuitively as assuming that this happened first, and then you want to calculate the probability that x22 would be 1, given that x11 already happened. So this together would give you the joint probability. As you can see, this is also equal to probability that x22 is 1 multiplied by the probability that x11 would be 1, given that x22 equals 1. So finally, one last property that we'd like to know is this. When you have two events, E1 and E2, if these two events are independent, then you have probability of E1 given E2 equals probability of E1. Similarly, probability of E2 given E1 would be probability of E2. This is because the knowledge of whether E2 happened or not will not affect the probability with which E1 would happen. That is because E1 and E2 are independent. We will use this later in a slightly modified form, but it would be a good time to just remember this. So now that we have recollected Bayes' theorem, let us talk about a Bernoulli experiment. So let us talk about a coin toss. So let me assume that I have a coin, and let me define a random variable x, which would be a result of a single toss of a coin. My random variable x would take the value 1 if I get a head, and a value 0 if I get a tail. A Bernoulli distribution is a probability distribution that defines the probability distribution of x. As you can see, it's a discrete probability distribution, and it can be represented like this. When we look at this, it might seem very complicated, but in practice, in reality, it is not. So what I've actually done here is I've actually made an assumption. So the assumption that I've made is that the probability with which x would be 1 is mu. So I've assumed that the probability with which a coin toss would result in a head is a number mu, and this would automatically mean that probability of x being 0 is 1 minus mu. So if you look at this, you can see that x can either take the value 0 or 1. So probability that x equals 1 given mu is mu to the power 1 multiplied by 1 minus mu power 1 minus 1, and you can see that this is equal to mu. Similarly, probability that x equals 0 given mu equals mu to the 0 multiplied by 1 minus mu power 1 minus 0, which is 1 minus mu, which is what we have seen earlier. So this is a parametric representation of the probability distribution for a Bernoulli trial. Now that we know what Bernoulli distribution is, let me introduce the topic of a likelihood. So let us assume that I have tossed the coin n times and I have obtained the outcomes x1, x2 up to xn. You may recall that any of the xi's where I equals 1, 2 up to n is either 0 or 1, where 1 represents an outcome of head and 0 represents an outcome of tails. And like earlier, we'll assume that probability of x given mu would be mu to the x multiplied by 1 minus mu to the 1 minus x. So I'm going to introduce another concept. We are going to assume that all the xi's are independent and identically distributed. We denote this by the short term IID. So what independent and identically distributed means is that when I say independent, it means that the outcome of xi is independent of the outcome xj for any I and j from 1 until n when I is not equal to j. This is the independence probability, and the identically distributed means that all of the xi's were sampled from the same Bernoulli distribution. Note that to do a maximum likelihood estimation, you do not require the samples to be IID. The advantage is that IID simplifies the computations a lot. So that is the only reason why we use IID. So let us denote D as a set of outcomes that we already have. Now the likelihood function is nothing but the probability that we have obtained D given that we know what mu would be. Or in other words, this is the probability of getting the outcomes x1, x2 up to xn given that we have sampled from the Bernoulli distribution with parameter mu. So since x1, x2 until xn are independent, this probability is equal to probability of x1 given mu multiplied by probability of x2 given mu, and so on. Now we have likelihood function as product of and as we already know, probability of x given mu was mu to the x multiplied by 1 minus mu to the 1 minus x. So substituting this formulae into our equation 1, we get so this is the likelihood function for the Bernoulli experiment that we have done so far. So from this you might have guessed what maximum likelihood estimation is going to be. So the way we are going to use maximum likelihood estimation is that we have already obtained the results D, and using D we are going to get the best estimate, which as of now is going to be called as the MLE estimate for us, because this is the method that we know the best now. Estimate of mu. I told you initially that x is distributed depending on the parameter mu, but we have never gotten a single value of mu. I told you that this is the distribution of x given a parameter mu. So what we are trying to do now is that since we have all of this data, from this data we are trying to get a particular value of mu, which would probably make getting this particular set of data the most likely. So what we want to do is maximize the probability of getting D given mu. So we are going to maximize L of x, and we are going to choose the value of mu that would result in maximum likelihood. As you can see, since L of x is a likelihood function, without going into too much details, you can see that the value of mu that maximizes L of x will also be the value of mu that maximizes logarithm of L of x. So the advantage of working with logarithms is, here you can see that L of x is a product of many parts. So when you actually take logarithm of L of x, you end up with sum of lot of parts. We are going to see how it is going to work now. So I'm going to take logarithm of the likelihood function and I'm going to maximize it. So this is why it is called the maximum likelihood estimation. Note that the product that we had earlier now has become a sum. This is what we have ended up with, and as we know, this is going to be equal to now how do we maximize the log likelihood function? So this is called the log likelihood function. So one way to maximize it is to take the derivative of the log likelihood with respect to the parameter that we want to choose and then setting it to 0. So we are going to do that now. So we are going to do differentiation of log of likelihood function over the parameter, and we are going to set it to 0. So we can see from here that it is going to be, the xi is going to stay as it is. I'm going to get a 1 over mu here, and this is going to stay as it is, and I'm going to get a 1 over 1 minus mu here, and then I'm going to set it to 0. So this simplifies to plus mu times 1 minus xi equals 0, and we are going to get xi minus n times